Hello, this is Phil Thomas from New Era Systems. Today I have on my cart an MT4000. The MT4000 is MCL 750 watt KU band TWTA. I received two of these for testing in the past couple of weeks. One of them had just about 0 hours on. This one has 12,000 hours. Both are extremely low hours. Now before I turn this on and start making noise, I'm going to look at some of the items that I'm using to conduct the test. Well, obviously I've connected a dummy load. This dummy load is probably rated for about 500 watts. This amplifier could potentially put out 750 watts. So that could be a problem with the dummy load. However, dummy loads can be overdriven, so to speak, if you put some forced air cooling on them. In this case, if I bring it up to 700 watts, it's only going to be for a second, so it's not going to really damage this dummy load. If I thought that I was going to do it for a long time, I would put a fan on it and start blowing air through these fins, cooling it. Because of course this is what a dummy load does. It takes the RF output from the amplifier and it turns it into heat. And in turning it into heat, you need a certain surface area of fins to be able to disperse that heat. And in this case, this dummy load is a little small. This cross-guide coupler is really rated a little lower than I would like it to be. It's from 12.75 to 14.0, and I'm going to run this at 14.0 today. And at 14.0, there is an attenuation of 50 dB. And that 50 dB is important for another reason. I'm using this Agilent power head connected to an Agilent power meter that I had to buy the other day because my last one got wrecked. And this power head will only take 20 dBm. If you drive it more than 20 dBm, you're going to cook the power head. And strangely enough, the power heads are more expensive now than the power meters themselves. So we've got to be very careful that we don't overdrive that. Let's just look at the math. We could potentially get 750 watts out of this amplifier. That would be 58.75 dBm. But that cross-guide coupler you saw a moment ago will reduce that by 50 dBm. So effectively, at full output from this amplifier, that power head is only going to register 8.75 dB. So I'm well within my 20 dBm range. Here are the components that we're going to use for today's test. On top you can see the Agilent power meter. That's going to register the output that we're getting from the flange of the amplifier. In the field we would have to have a modem, KU band up converter. I'm going to use this frequency generator, also made by Agilent, to put in 14 gig. And you can see it's already on 14 gig. This particular amplifier has a full range of 13.75 to 14.5, but I have a slight problem. The cross-guide coupler that I'm using for this test is a low frequency KU band coupler. It starts at 12.75 and it only goes up to 14.0, and so I'm only going to test at 14.0. And this is not a real test. The tests have been done. We know what this amplifier is going to do, but for this video we're just going to look at a very short version of that. The Agilent power meter is extremely flexible. One of the nice things about it is that we can set up the attenuation that's coming from the cross-guide coupler, and in doing that it immediately registers the correct power output. When first starting up an amplifier of this type, it has to go through a warm-up period to get the tube up to temperature before we even start putting any power into it. And the other thing to be careful of, if a TWTA has been sitting on a shelf for any period of time, it can absorb gas. Now these are supposed to be vacuum tubes, but no vacuum is perfect. So we have to be careful that we start to run them at a very low output so that any gas in there, any air in there, is going to be burnt off. This 750 watt KU band amplifier has a nice screen. It gives a lot of information on the screen. At the moment you can see the RF is on. There's no output because the frequency generator isn't generating any power, and so we're not getting output from the amplifier. That's how you turn it off. Now let's look at some of the things on here. Internal temperature, 26 degrees, fine. This is the helix voltage, very important. This is what drives the tube. Very high voltage is 10 kilovolts. Okay, you can see here the filament hours. This is not actually the time that it has been transmitting, this is the time that it's been turned on. So 12,349 hours seems like a lot, but it's not, it's extremely low. Many of these amplifiers will run up to 99 or even 100,000 hours. Now this is the beam on time. This is the period of time in hours that this amplifier has actually been transmitting. When I'm ready to start the test, I'm going to go onto the frequency generator, set it at a low level to begin with, set it at 14 gigahertz because this is where we're conducting the test, and then gradually increase the power, watching the Agilent power meter and also the front panel of this. The front panel is not that accurate. The most accurate reading is going to come from the power meter attached to the flange of the back. The bottom line here, the filament current, is very important. This is what we use more than anything else to show the health of the tube. For the moment there is no power being generated, so it's sitting at rest, and at rest it's 1.8 milliamps. That's a good low level, and we expect and we hope to see it. It's going to increase as we increase the power, but we don't want to see it run too high. If it runs up to 4 milliamps, 5 milliamps, that's perfectly okay. But we'll find out that in a couple of seconds once we start applying some power to this. I'm going to increase power carefully and watch the output on the power meter. RF is on, power level. As we increase it, you're going to see this number drop because it's not a power output level, it is an attenuation level. Admit that I had forgotten to press the transmit button on the amplifier. So as I was increasing the power, I wasn't seeing any change on the power meter. So I just crept over, pushed transmit, and now we're starting to see some input. At negative 31, we're showing 28 dBm, which is basically a watt. Now you can see the power start to move up. We're looking to be somewhere around 50 dBm. That's going to be a good high output from this amplifier, up around the 600-700 watt mark. Okay, change the display so that you can see wattage as opposed to dBm. But we're going to keep on increasing here until we get up to the 600-700 watt output level. I have to take it slowly now because a small increase in input gives a large increase in output power. And we don't want to put too much power into this tube. Way too expensive just to burn up by careless testing. I'm going to increase the power in a different way this time. I'm going to increase it in a digital fashion, and this gives me a much tighter control. Now I'm going to pause here for a moment and look over my shoulder and see what the output is, showing 58.3 dBm. Pretty good, but best of all, the helix current is shown at 2.1 milliamps. That is exceptional. Okay, as promised, I'm just going to take it up a little more. I can smell a little bit of burning coming from that dummy load that I've got on. And so I'm going to stop it at this stage. So if we look at the front panel of the amplifier, we're seeing an output of 57.9 dBm. 57.9 dBm is about 625 watts. So we haven't reached saturation, but 625 watts is very reasonable for a 700 watt amplifier. Okay, now before I start to smoke that dummy load, I'm going to turn things off and wrap it up, and basically this is the end of this short test today.